Alaikum Jami'an Marafra. Today we will start chapter 9, and which is the aldehydes and ketones nucleophilic addition reactions. As usual, we are going to start up with the Hypothermic Nature of aldehydes and ketones and the reactions of aldehydes and ketones, and finally our first preparation of synthesis of aldehydes and ketones, and finally reactions of aldehydes and ketones. Let's start first by explaining the nature of the carbonyl, which is a common functional group between the two. As you all know, as we have studied before, the carbonyl here, it's a polarized bond, and the polarization due to the higher electronegativity of the carbon compared to the oxygen, the carbon will carry a partial positive, while the oxygen will carry a partial negative. Of course, in principle here, so the carbon in the carbonyl is always electrophilic, which means it always has ability to react with nucleophiles. So in this case, whenever we have a nucleophile can add to the carbon and the carbonyl. And by the way, the reaction is very straightforward. When this adds to the carbon and the carbonyl, the carbon here cannot tolerate to be bonded to more than 4 bonds, and therefore this pi bond will break up to be given to the oxygen. So what we're going to get is this intermediate, and then finally with any acid present in the reaction, we are going to get a nucleophilic addition reaction. So that's in principle the whole reaction of aldehydes and ketones. Now, regarding when we compare the reactivity of aldehydes and ketones, as you have it in the slide, generally speaking, aldehydes they react toward this reaction, this type of reactions, are way much faster compared to ketones. And as it is explained in the slide, this is due to two reasons actually. The aldehyde, as you can see, since this is the aldehyde, it's attached to one bulk group, while the ketone is attached, the carbon and the carbonyl here, attached to two bulk group, which simply this will hinder the nucleophile from attacking the carbon and the carbonyl. So the first reason, because the ketone has a higher steric effect compared to the aldehyde. The second reason, due to the electron releasing ability of these R groups. As you can see, the aldehyde is connected to one R group, which simply decreases the electrophilicity of the carbon, while the carbon here has connected to two alkyl groups, which decreases significantly the electrophilicity of the carbon, and thus the ketone is less reactive compared to the aldehyde for this reason. Any questions so far? Is there any question? Please respond. All right. Now, regarding to the hypothermic nature, it's straightforward actually. We are not going to go through all of it, just to highlight the most important rules. Of course, we always have to find the longest continuous chain of carbon atoms, which contains these two functionalities. In the case of aldehyde, then the parent name, we have to replace the final E with the al, while ketone, we have to replace the final E with on, as you can see in these examples. And for the aldehyde always no need for designation of the location of the aldehyde functionality, because always the aldehyde functionality always takes number 1. For example, CH3, CH2, CH2, C double OH. This is always number 1. So it's 1, 2, 3, 4. So this 4. Therefore, we call this butanal. And the examples, I think, are straightforward in the slide. The issue here, which I would like to highlight here, if we have this as substitute, in this case, in case we have the aldehyde functionality present in a compound in the presence of another functionality which has higher priority, in this case, we will call this formyl. As a substituent, we will call it just formyl. For the ketone, C-O in the ketone, we will call it oxal. So these are the most important aspects of the nomenclature. Other than that, it's just straightforward nomenclature. The other issue here, whenever we have aldehyde attached directly, for example here, whenever we have aldehyde attached directly to a cyclic system, for example, here we have to call the parent name of the cyclic system, which is this case, it is cyclopentane. And then we have to add carbaldehyde for the indication of all of this functionality. So these are the rules for the nomenclature of aldehydes and ketones. They are straightforward rules we have just to follow, and these are examples. I think they are comprehensive examples which explain all aspects of the nomenclature of aldehydes and ketones. But yet, if you have any question about the nomenclature, please ask now. Otherwise, just say no question. Any question about nomenclature of aldehydes and ketones? Is there any question? Where are you? I suppose, okay. So we'll just move to the next aspect, which is the synthesis of aldehydes and ketones. There are several methods available for us for the synthesis of aldehydes and ketones, and most of them, or all of them actually, we have already discussed them before. For example, all right, aldehyde. Regarding for the question of Al-Harith is asking why the OH, the alcohol, has higher priority than ketone. That's actually not true, Al-Harith. The ketone has higher priority than the alcohol. So I don't know where did you see these examples. From the examples what we have in there is no such a case actually where we have here, for example, the first question, Al-Harith, if you check the first example, you can see that the ketone has higher priority than the alcohol. And therefore, the alcohol here, we call it hydroxy, while the ketone is the parent name. Is that clear, Al-Harith? All right. Let's move to the synthesis. What are the synthetic methods used for the synthesis of aldehydes and ketones? And as I said, most of these methods we have already discussed them in the previous chapters, but we're just gonna go through them very quickly. First method for the synthesis of aldehydes and ketones, which is very fundamental in here, which is by oxidation of the corresponding alcohol. In other words, aldehyde can be synthesized from the oxidation of the corresponding primary alcohol, while ketone can be synthesized by the oxidation of the secondary alcohol. As you can see it in the slide, we have just to be careful for the choice or the selection of the oxidizing agent. In the case of the aldehyde, it's extremely important to use PCC to stop at the aldehyde level, while for ketone, doesn't matter, any oxidizing agent would be fine. So that's actually regarding the synthesis of aldehydes and ketones using or starting from their corresponding primary or secondary alcohol. Now, for ketone, there is another method which we have synthesized, we have explained in chapter 4, which is by addition or hydration, addition reaction to terminal alkyne. In principle, this always gives the corresponding alpha-methyl ketone, as you can see it, according to Markovnikov addition rule. Another method for the preparation of ketone, which we have discussed in chapter 5, which is for the synthesis of Friedel-Crafts acylation of benzene. So remember, Friedel-Crafts acylation only works when we have aromatic system. Doesn't work for any aliphatic system. For example, if we are asked to prepare this ketone starting from cyclohexane, oh sorry, let me just make it as if maybe that was a mistake actually. If you want to start from cyclohexane and you want to prepare this, you want to prepare this ketone we cannot prepare it via Friedel-Crafts acylation. For example, to use acetyl chloride in here in the presence of aluminum chloride. This does not work. Why? Because this reaction only works for aromatic compounds, does not work for saturated compounds. So please be careful about such a case. The method here, which you have it in the slide, for the preparation of Friedel-Crafts acylation for the preparation of ketone, only works if we want to start with benzene systems. So that's actually the thing which we have to take into consideration. Another reaction actually for aldehyde, not for ketone. Now, in principle, before talking about this, in principle, please remember my words carefully. Any reaction works for aldehyde, it will definitely work for ketones. That's for sure. So aldehydes and ketones work always similar ways. But the only reaction which they simply differ actually from each other is the ability of the oxidation. In other words, aldehyde, as you can see here, if we oxidize it, it can be oxidizable to the corresponding carboxylic acid, while ketone, regardless of the oxidizing agent, it will not oxidize further. And that's actually the only difference of the reactivity between aldehydes and ketones. And that's why we may use this difference in the reactivity as a chemical test. So, in order to distinguish the aldehyde from the ketone, since they are reacting similar, we use the Ketones test or Ketones reagent. And the Ketones test or Ketones reagent is silver ammonium hydroxide. This is an oxidizing agent. When we allow this Ketones reagent to react with the aldehyde will be oxidized to the corresponding carboxylic acid, and of course based on the condition, if we're talking about basic, that will be carboxylate. And in this case here, we will get also a silver as a silver mirror. It will be depositing on the test tube, in the walls, in the interior walls of the test tube. So this reaction actually can distinguish aldehydes from ketones, and at the same time it works as a distinguishing test between aldehydes and ketones. Is there any question, please, so far? Any question? All right, perfect. Thank you. All right. Now, for this slide, which is simply the reactions of the carbonyl containing compounds with the reducing agents, I think we have discussed this very many times in the previous chapters. The only thing we said, we do have two major reducing agents in organic chemistry. We have the powerful one, which is the lithium aluminum hydride, which is capable of reducing all carbonyl containing compounds to the maximum power, to maximum level of the reducing level, while the sodium borohydride can only reduce aldehyde or ketone. So we are not going to discuss this slide because we have discussed it many times. Now, there is another reaction which aldehydes and ketones can react with, which is hydration, which is the addition of water to aldehyde or ketone. This reaction actually is not a practical reaction, which means we cannot get a stable product actually. We are just gonna comment on this as addition reaction. So in principle, if we have aldehyde or ketone, I'm going to abbreviate it by this way, which just to refer, doesn't matter if I talk about aldehyde or ketone. Then with water, the water will add itself to the carbonyl, and therefore we will get a diol here. This diol is not stable. It will simply go back to the original aldehyde and ketone, and the only or simply the rare example which we have shown you in the slide which is the preparation of the chloral. The chloral is a staple product which is actually used in our daily life as a medicine, as a sedative or sleep medication in these days. Now, another reaction of aldehyde and ketones, which is their ability to react with alcohol. So, in principle, if we have aldehyde or ketone, and we allow it to react with, I'm just going to use a different color for the alcohol now. If we allow it to react with 1 mole now with alcohol in the presence of H plus as a catalyst, what we are going to get is the addition of, addition of the alcohol, and in this case, COH, and then I'm just going to use another color here, OR. Do you see it? Now, this is for the reaction of the first 1 mole. This functionality, we call it hemiacetal. And please just check here carefully what's the hemiacetal. The hemiacetal is a carbon connected to OH and OR. See, this is simply what we call it hemiacetal. Now, if we allow this hemiacetal to react further with another mole, I'm just going to use again different color. So another mole of alcohol in presence of H plus. What we are going to end up with, C OR, and then R or H. Here we call this acetal. And again, the acetal, we have to recognize it nicely that the acetal here in this case is carbon, as you can see, attached to 2 alkoxy group. Hemiacetal is carbon attached to 1 alkoxy group and 1 OH. Acetal, carbon attached to 2 alkoxy groups. So please be aware how to recognize the acetal and the hemiacetal. It's worth to say that actually these reactions are reversible, so we can always convert the acetal to hemiacetal and then the hemiacetal back to their aldehyde or ketone functionality. And that's why actually the major use of this reaction, as you can see in the next slide, that the major use of this reaction is we can use the acetal formation as a protecting group of 1 aldehyde or ketone functionality. And then we can do the reaction for the rest of the compound. And then we can remove this acetal and then we can end up with whatever we want. The example which we have, or similar example to what you have in the slide, for example, if we have this challenge, if we want to convert this functionality or this compound into that. So, how to convert this compound into that. As you can see, Salama, regarding for your question about the stability of acetal to hemiacetal, actually it's relatively speaking issue. It's here the stability we cannot really now discuss it in details, the stability of hemiacetal or acetal. But in principle, what you need to know that this reaction, either for the formation of acetal or hemiacetal, they are reversible. So we can form them, we can reform them. That's actually the most important aspect of it. So both reactions are reversible, Salam. Is that clear? Sure. All right. So as you can see here, to answer this challenge, we check this compound. What functional groups we have? We have ketone, we have carboxylic acid. Now, we need to reduce, of course, it looks like we have to reduce this functionality. Now we have two options, right? Because the only two reducing agents which we have discussed in this course are the two, the lithium aluminum hydride or the sodium borohydride. Now, if we use lithium aluminum hydride, maybe I have to choose another color because the green color may be not that much clear. If we use lithium aluminum hydride, what we are going to get, the lithium aluminum hydride is powerful reducing agent. It will reduce both functionalities. So of course we are going to get or end up with this compound, which is different than what we need. So this definitely is not correct. Now, if we use directly sodium boron hydride, what we are going to end up, we are going to reduce the ketone, but we cannot reduce the carboxylic acid because, as we explained before, sodium borohydride is very mild reducing agent. So this again does not give what we want. So both ways they are not working. So that's actually here it comes the indirect method here, which is simply the use of acetal as protecting group for the ketone. Then we do the reduction, then we remove the acetal to end up with the product. Do you follow the tactic here? Do you see the logic here why we couldn't do it direct? Now, one way to solve it, it is as you can see it in your slide or this example, simply to protect the ketone. We need to protect the ketone here. If we can protect this, we can reduce that. You follow me? Then we can remove the protecting group. One way to do it, to convert this into acetal. And another way to convert it to acetal, because as we have explained in the previous slide, we can form the acetal by reaction of aldehyde or ketone with 2 moles of alcohols. Another way, simply to react with diols, because it's the same similar idea. As if here we have 2 moles of alcohol, but in the same compound. In this case, what we are going to get, what we call it cyclic acetal in this case. You follow me? So here you can see, in the presence of H+, of course. As you can see here, we have converted the ketone into acetal here. But of course, this is a special one, which we call it cyclic acetal. Can you see it? You follow me? Now, once we protected this, now we can make the reduction. The lithium aluminum hydride now, it will not affect this because this is not ketone anymore. It is protected ketone, what we call it acetal. The lithium aluminum hydride can now reduce the carboxylic acid and converted it into its corresponding primary alcohol. Of course, this is always after 1 and second with H+. And then finally, we can remove the acetal by just adding excess of water in the presence of H+. We can synthesize our target product. Do you see it? So the major use actually for the acetal formation is simply to protect aldehyde or ketone functionality from reacting in certain reaction, and then remove it after we finish our bonds. Is there any question about this specific example or the example that you have written in the slide? Any question, please? All right, perfect. Now the last topic here, which we are going to discuss, which is the use of, before the last topic, we have the Amine formation. And the Amine formation here, It's aldehyde or ketone, as you can see. When they react, again, I'm going to use a different color now. When they are reacting with any amine or primary amine, let's say primary amine or ammonia, you follow me? What we are going to get, R, C, R or H, and then double bonded to N, R plus H2O. Can you see it? So, in principle, any primary amine, which means any NH2 attached to anything, it will react with the carbonyl in the aldehyde and ketone to form this new type of bond. This bond here, the C, the bond N, we call it imine bond. It's not amine, we call it imine bond. It's a very straightforward reaction. Any primary amine, in other words, any NH2 attached to anything, when it reacts with aldehyde or ketone, will form the imine bond. Clear? Is that clear? All right. Now, the last reaction now, which is the Grignard reagent and the Grignard reactions. The Grignard reagent, it's a special type of organometallic compounds, which we call it organometallic, RMGBR. This type of compound, we call it organometallic compounds. And why we call it so? Because we have, as you can see, a metal, in this case the magnesium, connected to R. R here, any carbon. You follow me? Now, obvious, when we check carefully the polarization of the bond, what we have to notice that the magnesium, since it's a metal, it's the element which can or which has the ability to lose electron. It will carry a partial positive, while the carbon will carry a partial negative. As you can see, this is a very rare example where the carbon here can carry negative charge. In all of reactions, whatever we have discussed so far, always carbon was carrying a partial positive. This is the only example where we have the carbon is carrying a negative charge here. And of course, since this is true, in this case here, the first example here, any negative ion can react with H+. So the first reaction, what we can guess, that this here with acidic hydrogen, can be converted into RH. It can react with any acid. Secondly, it can also react as a nucleophile, as we will see in the next slide. Do you follow me? This is actually the major fundamental aspects about the organometallic compounds or the Grignard reagents. How we prepare it? We prepare it very simply by reacting any haloalkane or alkyl halide, RX, with magnesium in presence of ether. So here there is no limitations. The R here can be anything, as you can see it in the slide. It can be primary, secondary, tertiary, can be aryl, can be vinyl, can be any carbon containing compound, wherever it's attached to the halogen. In the presence of magnesium, presence of ether, we can form this. Now this here can be ready to go and to react with the aldehyde and ketones, as you will see in the next slide. Is there any question about specifically this slide before the next slide? Just about the organometallic compounds, about the formation of the Grignards, about the polarization of the bond. Is there any question? If there is any question, please ask now. Any question? Wonderful. Today is easy going. There is no questions at all. I just noticed that. All right. Okay, perfect then. All right. So you see, now we are going to discuss the behavior of the Grignard as a nucleophile in the next slide. And in this next slide is a very important slide actually. I just recommend you to take care of it. that the Grignard can react with different carbonyl compounds, and it will produce different other different compounds too. So for example, the Grignard, and we are going always to abbreviate the Grignard by R, regardless of whatever this R is. So RMGBr, for example, plus CO2 always gives RCO2H, which is carboxylic acid. As you can see, we can elongate the R by CO2H. Do you follow me? So that's why actually, if I ask you how to convert this compound, or cyclopentane, suppose, to this compound, C-OOH. The first thing what you can think of simply we as if we want to elongate this carbon with carboxylic acid functionality. One way to do it is simply to allow one of the alkyl group to be a Grignard and simply to react it with CO2. That's it. So the question is how to convert this into Grignard. As we know, since this is saturated organic compound, then the only reaction which is available for us is the halogenation. Once we have halogenated cyclopentane, then by reaction with magnesium and presence of ether, we are going to get or convert it into the magnesium, the Grignard reagent. You follow me? Now, when we allow this to react with CO2, we are going to get the target product. Very straightforward, very easy going. Can you see this example? Yeah, so this is just to show us just the easy of this reaction. It works very easy actually for the preparation of different carboxylic acid. So check the first reaction, Grignard with CO2 always increase the carboxylic acid. Is that clear, the first reaction? Any question about the first reaction? Is there any question? Perfect. The second reaction is a straightforward reaction too. So we can simply, I'm just going to erase this if there is no question. So the second reaction, when we allow the Grignard to react with one type, special type of aldehyde, which is the simplest aldehyde ever, which is the formaldehyde, then what we are going to get RCH2OH. See, as if we are elongated the R here with CH2OH. You follow me? Similarly, for example, if I ask you how to convert benzene, for example, into this benzyl alcohol, CH2OH. Supposed to be straightforward method here now, because simply if we can convert this into Grignard, we can allow the Grignard to react with formaldehyde, then it will definitely produce the benzyl alcohol. Now, how to convert this into Grignard? It's two-step. First, bromination by electrophilic aromatic substitution reaction, which is bromine in presence of iron bromide, for example. Then, secondly, by reaction with reaction with magnesium to convert the Grignard. Then, finally, reacting with formaldehyde. So, in this case, we can react it by bromine presence of FeBr3. We can convert it into bromobenzene. And then here we can react it with magnesium and presence of ether. And then finally, by reacting with formaldehyde, always secondly with H+, then we are going to get the target product. Clear? Is that clear? How to always reaction of Grignard with formaldehyde converted into a primary alcohol. Always the Grignard, whatever the Grignard is, reaction of Grignard with aldehyde any aldehyde, then it will convert it into secondary alcohol. Reaction of Grignard with any ketone will convert it into tertiary alcohol. I think these are this method, actually, the use of Grignard method is a very, very important method for the organic synthesis, because it enables us to prepare a wide variety of different functional groups. Is there any question so far about this slide? All right, perfect. With that, we are done with this slide. Then if there is no any further question, I would like to thank you all for your attendance, and we'll see you inshallah next Thursday for the exam. Is there any question? Salama, we are going to include chapter 7, whatever we discussed in chapter 7. Here, I know I understand your question. This here will be included only in the final exam, not in the chapter 7. Is that clear, Salama, and everyone there? So it will not be part of our exam, but it will be definitely part in the final exam. All right. Okay, guys, I would like to thank you very much for your attendance. Inshallah, I'll see you very soon, and stay safe. Ramadan Kareem.